I'm a senior software developer and I specialize in .NET. I have been using a library called SignalR for quite a while. And in one of my projects I have used it to connect clusters of IoT devices together. So in this stream I will show you how to enable this, how to make several IoT devices work as if it's a single device, as if it's a single distributed application. One of the applications in a real-life project for that was a train station. So basically, different devices were positioned at different platforms of a train station. And whenever one of them was playing announcements for a train, the other devices knew that an announcement was being played. They knew not to interrupt the announcement. So for example, if one of them was announcing a train, then the other devices would not play no smoking announcements or anything like that. If you don't know what SignalR is, it's a library that enables you to communicate between the client and the server in real time. Normally, for this kind of communication, you would use something like a WebSockets protocol. WebSockets is a two-way communication protocol that starts with WS or WSS if you are using SSL. In C# in particular, this is how you would normally write WebSocket communication, which is quite complex. And with the SignalR library, the process is very simple. So this is what SignalR client looks like. It's just it looks like it's just calling remote procedures, and the SignalR server looks like this. So all of this communication, all of this byte transfer via WebSocket gets abstracted away by SignalR library, and this is what makes it really convenient to get clients and server communicating with each other. SignalR comes as a default with .NET since .NET Core. You don't have to enable it as a separate library. So for example, my server-side project in here, if I open the project file, it does not have any dependencies. It's just pure .NET 5. All you have to do to enable it is just add SignalR in configure services method. And then you have to register your hub class on the server side, which in my case is device hub. This particular bit of code is a simulator, is a very simplified simulator of distributed application that is very similar in its structure to the one I've built in real life for that train station. So we have this WebSocket project just to demonstrate the difference between SignalR and WebSocket. But what's important is this console application, which mimics the application that will go onto the IoT devices in the field. Each of the IoT devices has its own identifier, and normally in real life it would be something like a serial number. And then you would have some config that will come with it. In this case here, because it's a console application, it will prompt you to enter those details because it just mimics the real application. But in a real application, when you launch it, there will be serial number of the device itself. There will be, in configuration file, there will be location of the device. And then, there's area and there's location. So area, in the context of that particular project, was a train station, while location was a platform. So each device, all devices in the area were acting as a single distributed application, while each location represented a single device. And then there's some code that will enable the SignalR client to connect to the server. In our case, I'm just using localhost because this is where my server will reside if I launch it. But obviously in real life it's going to be some IP address or a URL of the actual server. Then we're registering our events. So whenever our server side because it's a two-way communication. Our server can call our clients, and our clients can call our server. Whenever our server will call receive work, we will execute do work method. And whenever it calls receive work status, it will do this. So there's a Boolean variable here, hold of work. In our case, this hold of work variable is used to let the devices know that they should not be interrupted. So whenever the first device receives request to do some work, in our case, our code is just waiting. But in a real life scenario, it will start playing audio. When it starts playing audio, it will broadcast to the hub that controls all the other devices that audio started playing. And it will set receive work status to true, so no other devices in the area will attempt to play audio. If this device is playing audio and another device in the same area receives a request to also play audio, this other device will hold off until this device has finished. And this is what this code does. It will just carry on checking whether hold of work has not been cancelled, and only then it will start playing its own audio. Or sometimes you will get devices to disconnect for whatever reason, and this is why we also have the timeout. So if you know that any audio announcement should take you less than a minute, and hold of work has still not been set back to false, it will set it back to false if it times out. On the hub side, we have these various methods here. So if we'll go back to this code, when we connect to the hub, first we call start async, which starts our hub connection, and then we call this method with the following parameters: identifier, area name, and gate number. Whenever we receive those, we register a serial number against connection ID that is provided by SignalR infrastructure itself. A connection ID is a string field, but it's a GUID format, and it will be unique for every connection. SignalR itself identifies each client by connection ID. But we need something that is human readable, so in our case, device ID can be something like a serial number. I have this static helper class to map the two. So for example, we can pass connection ID and we can get serial number back. Or whenever we disconnect, we can remove the mapping between connection ID and the serial number. And then we also map device to location. Once again, location is used as a unique identifier of the device. Of course, you can replace device at a particular location, but it still forms part of the cluster. And we are adding device to a SignalR group, because SignalR has inbuilt concept of groups. And in our case, we're just adding a unique connection ID to a particular area name. And this is how the device knows how to broadcast, or which other devices to broadcast its connection status to. Actually, it's plain status too. So if we go back to our client, whenever we start playing, we broadcast work status with either true or false. And this is what happens on the device hub. We receive it. We receive the area name. Then the Boolean field of working, the Boolean parameter of working would be either true or false. And then what we do, we send this message to every single client in the group that matches the area name. And then each client will have this application running. It will have receive work status event triggered. And whichever working is set to, it will set hold of work to that particular value. And then whenever client disconnects, we just remove it from the group. So what would happen on server side in real life is some data feed will constantly keep coming to the server application, and the server application will react to the events. So for example, there will be some logic on the server side, which will determine when to play which train announcements. So for example, certain announcements will be played 5 minutes before their arrival. It will be a detailed announcement saying that such and such train that is due to come to a particular destination is going to come at platform 2 or 1 or whichever number it is, and it will announce all the calling points as well. Then there will be another announcement which will play just 1 minute before the arrival of the train is due, and it will be similar, but for example, it will not call all the calling points, so it will be shorter. In our case, we are just mimicking all of this. Our application itself is ASP.NET Worker. And as a work service, we have an event scheduler. So basically, worker service is a type of service which is hosted inside of ASP.NET application, which just keeps continuously running until you stop the application. Also, with SignalR, you can pass hub context into any place that is outside the hub, and that will allow you to send messages to hub clients from outside the hub. So in here, we just have some hard-coded data, but in real life it will be a real data feed. There will be some kind of listener that receives the data. And in our case, we are doing the following. For each location, so in our case, locations will be platforms 1, 2, 3, and 4. We get the connection ID because SignalR, as I said before, does not have the concept of identifying client by some human-readable attribute. It's got its own connection ID that it has assigned to a connected client. So if connection ID was found that matches this specific location, if there was a device registered for that location that is currently connected, then we just send this message to receive work method, which is receive work. And to recall it, it's a do work method that gets triggered. So our first method on the first device gets triggered. And now what's happening is it will just sleep for a minute. So let's pretend that it's playing audio for this duration of time. And before it started playing audio, it has broadcasted to all the other devices in the group that is busy. So now, if we go back here, it will then go on and try to send the message to device at location 2. And what will happen then is the device at location 2 will receive this message. But then, because the first device has not stopped playing its audio has not stopped doing its work yet. Hold of work will be set to true. So it will just carry on going through this loop until it either times out or hold of work has been set to false by receiving work status by the first device triggering this method. And only then this second device will start playing. Also, what I've done here is I've actually split those different locations into two different groups. So what this means is that if a device at location 1 starts playing audio, and then the message is sent to the device at location 3, then the device at location 3 will start doing work straight away, because they belong in different areas. They are essentially different clusters. So locations 1 and 2 interact with each other, and location 3 and 4 interact with each other. But those two clusters don't actually interact among themselves. So there are 4 devices, but there are 2 separate clusters. There are 2 separate applications. This, of course, is a fairly simplistic solution as well, because it's not always the most efficient thing to do, to send the messages to all devices in the cluster via the server. Even though it works, it's fairly simple to write code for it, and it's fairly simple to demonstrate. But in real life, what you would normally do is, when you set up a cluster of IoT devices with SignalR, you can actually host SignalR Hub on the devices themselves. And in that configuration, there will be one device that will nominate itself as the master device or the main device. And it will be only that device that will communicate with the server directly. The rest of the devices in the cluster will communicate only to that device. And all the messages to other devices will be transferred via the main device. This way it will be much more efficient. So whenever any particular device will not need to indicate that it's busy to all the devices in the cluster, it does not have to talk to the server. It will then only have to send its signal to the main device that hosts its own SignalR hub. Because the beauty of .NET Core and ASP.NET is that, well, ASP.NET is nothing but some extra plumbing on top of console application that can be hosted absolutely anywhere, on absolutely any operating system, and pretty much any CPU architecture as well. And this is why it's fairly suitable for IoT devices. So as well as you can deploy it on a server, you can also deploy it on a single board computers. And whenever you start building your IoT cluster, a good place to start is with Raspberry Pi, because Raspberry Pi is very cheap. If you are using it for production purposes, then you probably would want to change it for something else later on, something more robust. But initially, Raspberry Pi is a very good device to get yourself started with. And it is capable of hosting ASP.NET Core and SignalR Hub. Another thing about SignalR that is quite good is that it doesn't necessarily have to operate with WebSocket protocol, because WebSocket is not available everywhere. There can be some network restrictions that will prevent it from working properly, because WebSockets essentially establishes persistent connection between client and the server. Unlike HTTP, it does not work on the basis of request-response protocol, and that's precisely why it can send messages both ways between client and the server. With WebSockets, you just send the initial handshake and then the connection becomes permanent. So server can talk to client, or client can talk back to the server. With HTTP it's different, of course. Client always sends the request and server always sends the response back. With SignalR, if WebSockets is not available, what can happen is that those can be replaced by server-sent events, which is a different protocol, or long polling. Long polling essentially is HTTP. Long polling works by sending a request from the client to the server, and then client will basically just wait for the server to send its response back, instead of just timing out immediately. But from the perspective of SignalR, if you are using long polling in it, your code will be pretty much the same. As a developer, the way you write code is as if you are calling remote procedures on the client and on the server. It's as if two pieces of code from inside of the same code base, inside of the same application, are talking to each other. The only different thing that you have to do to make sure that you are using long polling instead of anything else is reconfigure your hub connection. With URL method has some overloads. And one of those parameters you can put as well as URL is HTTP transport type. So, as you can see, if you don't specify anything, then the default transport type will be WebSockets. This code here is exactly the same as if I've never entered the second parameter. Then the second best, well, WebSockets is the best one, and the second best one is server-sent events, which is also its own protocol. A client establishes connection, and then it's the server that triggers subsequent communication. And then the third one, the least efficient one, is long polling. So if you know that you're working in an environment where either WebSockets or server-sent events are not supported, you just configure your client connection to connect to long polling. But everything else will stay the same. All of this syntax will stay identical to it. Nothing will change on your hub either. This code is available in GitHub repository, but I have also published a course on Manning, which is a live project. In this course, you will build your own application like this, but the purpose of that particular application will be to enable same kind of communication, but at airport. So imagine that you have airport with different gates located close to each other, and there are also some announcements about arrivals, departures, and gate closures. And just like at a train station, you don't want different devices to overlap, to talk over each other. So the logic is exactly the same. You separate devices into different areas. Different areas has numbers of the different locations. Each location has a single device. and each area acts as a cluster. So principles are the same, but there are more details as well. The project takes you through several different stages of the process, and but by the end of it, you'll know how to build application for your own purposes, for your own projects.